Hello, this is Concrete Pattern, the fourth lecture for your RCC. And the problem is that singly reinforced beam and singly reinforced beam we have we need to get the safe load and ultimate moment capacity for this section. Ultimate moment capacity for this section. So we have four number of bars that are having diameter of 25. So 425 bars, and 600 is the overall depth. 600 is the overall depth, and 300 is the width of the cross section. Effect cover is given to you as 50 millimeters, and your yield what you call as yield stress for the material for the steel is 250 megapascals. We can convert that 250 megapascals, and FCK we have 20 megapascals. Effective length for the simply support beam is 6 meters, and we had to apply that UDL live load, and its half weight is also there. So we had to see how much live load should we apply on the beam. So it's similar to that of a previous problem. We had some problem 6 we had earlier. So that's similar to that. Let's go for that one. Let's take that. I would say your effective depth would be equals to 600 minus 50. Effective cover, that's finally 550 millimeters. Now first step is that get the value of XU, that is 0.87 Fy AST, 0.87 Fy AST, 87 Fy AST, pi by 4, 25 square, and number of bars are 4, and divided by 0.36 FCK into B. So that XU equals to 197.71 millimeters. Now we need to get the actual that limiting condition for that neutral axis, actual limiting. That is K times D. K times what you have, D. Then 0.53 is the value of K for your mild steel. 0.53 into D. So that is value equals to 291.5 millimeters. And by comparing that XU and XU limiting, you can tell that this value is less than XU limiting. So our XU is less than XU limiting. So section is designed as under reinforced section. So your section is under reinforced section. So if the section is under reinforced, that means you can solve that moment of resistance. So your ultimate moment resistance or ultimate moment capacity, that we can say that is your MU, that corresponds to XU actual. XU actual. So let's try that equation. 0.36 FCK B and XU actual 197.71, 197.71 XU actual. Okay, 0.36 FCK B XU, and we have that lever arm D minus 0.42 XU. Okay, so your moment of resistance is equals to 199.42 kilonewton meter. Now our load should be such that this is safe loads. Our safe loads should be such that they would cause an external bending moment, factored external bending moment, and that value should be less than your limiting moment of resistance. And in this case, we are not talking about limiting moment of resistance. We are talking about that actual condition, because our section is under reinforced. So we have to take that, not with respect to limiting condition, we have to take that that moment of resistance corresponding to actual actual, that's corresponding to under reinforced section. So we don't have to write MU limiting here. I would say I had to equate now directly. I had to equate directly because I know that value of MU corresponding to XU actual. So I had to substitute directly. We can say the value of W would be corresponding to MU at the rate of XU actual. So let's substitute the value of MU 199.42 kilonewton meters. Then from this side we have to substitute the value of W. We don't know the value of W. Let's keep the W as W safe. It's because of all W dead plus W live load plus dead load, and but we are saying that this is safe value, and we have this length of L square by 8 into 1.5, load factor 1.5. So finally you would say W safe would be equals to, W safe is equals to 44.32 kilonewton per meter. Now it was given to you that dead load, it was given to you dead load is equals to 15 kilonewton per meter square. And then actually it's saying that per meter square, if you have this beam, if you take per meter square of the section, if you take 1 meter strip, and we have the cross section as B into D, we have this width of B, and we have this length of 1 meter. So per 1 meter, per 1 into B area meter square, you have this dead load equals to 15 kilonewton per meter square. That means that actual dead load intensity would be 15 into B kilonewton per meter. That we also can solve that by gamma concrete into width of the cross section and depth of the cross section. You would get same value. You would get the same value. If you substitute the value of gamma equals to I think 25. If I substitute 25 kilonewton per meter cube, and the width we know 0.3, and the depth we know 0.6, that would be also equals to 4.5 finally kilonewton per meter. 4.5 kilonewton per meter. 4.5 kilonewton per meter. 4.5 kilonewton per meter. That means the safe live loads we can have, apply on the beam, that is 44.32 minus 4.35, that's equals to 40. Yeah, see, actually the safe loads was equals to 29.54. So finally 29.54 minus 4.35, that's 25.04 kilonewton per meter. In the problem 6, we have there the condition was that your XU was coming to be greater than XU limiting. The difference between this problem and the previous problem, that problem number 6, we have, in that case, we have our actual neutral axis location was greater than XU limiting. So we said that this section was under an over-reinforced section, and in that case we said your external bending moments should be lesser than that limiting condition, because our moment was corresponding to limiting neutral axis location for that, because the section was under over-reinforced. So we had to limit our moment capacity to limiting moment of resistance. We don't want to use those actual moment of resistance. We don't have to go to that, because that would make the steel unutilized because of over-reinforced section. So in that case we equated that with, that means we equated to limiting moment of resistance, and by equating that lesser or equal to, and this lesser means it would ensure URS, it would ensure the section becomes, finally your load should be applied such that finally your section becomes under reinforced. And in this case our XU was greater than XU limiting. Yeah, XU was lesser than XU limiting. It was directly acting as an under reinforced section. So we can directly equate. There's no worries. We would say external moments should be equals to actual moments we have from this one. Then we say this should be your safe load. We can have safe load. Okay. Let's go for problem 9. Problem 9. We can have problem 9. Okay. Problem number 9. We have to. This problem is about the design of simply support beam. This is the design of simply support beam. Design simply supported beam of length LA, effective length equals to 7 meters. Live load 45 kilonewton, supporting this live load 45 kilonewton per meter, and our width of the cross section is fixed. Your cross section width is fixed. So B is fixed. It is given to you. B is equals to 500 millimeters, and we are using M30 and FE 500 megapascals. FE 500. Okay. Now we have to design. That means we need to get, if the B is fixed, that means we need to get now diameter, depth of the beam, total depth of the beam, and we need to get the AST. So we don't know the value of D. We don't know the value of D. We don't know the value of D, and we don't know the value of what is the steel, what should be the area of the steel provided, and which of the bars we are going to use. What is the diameter of those bars we are going to use. That we need to calculate for this problem, design of simply support beam. Okay, let's try to get that problem. Okay. So let's see what is the total loads we are applying on the beam. We have this beam. Let's see. We have this simply support beam of length 7 meters, and there's some UDL acting. That is because of dead load and live load. Let's say there's some dead load, there's some live load, and let's call all that load as W all. And because of that, we say bending moment maximum would be corresponding to WA7 square by 8. This is your maximum bending moment, and this is a safe value. Now, if you apply that factor of safety, load factor, what you call as load combination factor, 1.5 for dead load and live load, 1.5 dead load plus 1.5 live load, then finally I would say bending moment, external bending moment factor, that we represent as MUE. This is your external bending moment, that is factored bending moment external because of external moment, live load and live dead load loads. Okay, that we can calculate as 1.5 times WD plus W live, then L square divided by 8. So once it's given to you that live load is 45, live load is given to you as 45, and dead load is given to you as gamma concrete into B into D. Now we don't know the value of D. Everything we know, we don't know the value of D. Actually, it should be capital D here, capital D. So we don't know the value of D. What should we take the value of D equals to? What should we take the value of D equals to? What should be the value of D we have to take? So a general thumb rule is that we have, let's try that. A general thumb rule that D is usually span by 10, effective span by 10. If your effective span is 7 meters, 7 meter by 10, that is 0.7, that is 700 millimeters. So if you assume by this, if you start by this property, by this what you call as thumb rule, if you say that overall depth of the beam is around 700 millimeters, let's try to have this value here. Let's try to substitute that value. Then after that, I would say your gamma C, let's say the gamma C is 25 kilonewton per meter cube, and your width of the cross section is 0.5 meters, and your depth you assume it to be equals to 0.7 meters. So this value is equals to 0.7 into 0.5 into 25, 8.75 kilonewton per meter. This is the dead load we have, and self weight 8.75 kilonewton per meter. So finally, I would say overall value of this one, this was your 7 square meter square by 8. So I would say 8.75 plus 45 into 49 divided by 8 into 1.5 factor, 493.8. That's 493.8281 kilonewton meters. So this is the moment MUE, that's external bending moment, factored external bending moment. I have to say this should be see, how should we start the problem? So to start the problem, our condition was that your external bending moments, they should be lesser than limiting moment of resistance. This is the start of the problem. How can you start the problem? I would say I would ensure that your limiting moment of resistance is even greater than actual moment of resistance. That means if there is actual neutral axis somewhere, I should ensure that at least my section is balanced. At least my section should be balanced. Once I got that particular value of depth required, Then after that, I can increase the depth such that my section becomes under reinforced section. Let's try to have that. Let's try to have that. Let's try to have that. So if the external bending moment is 493, sorry. So if there is some external bending moment, that should be lesser than Q times FCK BD square. And we already know that what should be the equation. Then finally we write that D should be root of MUE by Q times FCK B. So you substitute those values. I would say 49. That's 493.8281 10 to the power 6 Newton millimeters divided by Q. What is the value of Q for the steel that is a Fe 500? Do you know the value of Q? Is that 0.133? Yeah, you can see that your value of Q is 0.133 corresponding to Fe 500. And FCK was given to you M30, yeah, M30 is there, M30, and this was megapascals. And value of B, it was given to you as value of B was 500 millimeters. So you would get a depth of the section required. That's around 493.82821 into 10 power 6 divided by 0.133 into 30 into 500 divided by 10 and root of that 497. So that it says that the D required should be for the limiting, it means for the limiting condition D required is 497.52. But if I want that my section should be, this is for limiting condition, for balanced section, limiting condition. If I want for under reinforced section, my D should be greater than 497.52 millimeters. So then I generally increase it by some value, 50-60 millimeters. Let's say that my depth is 550. Let's say I'm going to adopt that D value equals to 550 millimeters. Then finally I would say there is some effective cover. There will be some effective cover of 50. I assume that the effective cover is 50 such that your overall D would be 600. Overall D is 600 millimeters. So initially I had assumed that capital D was 600. Capital D was 700 from this thumb rule that span by 10 700 millimeters. I got that D was 700 millimeters, but I had to revise that one. So finally I would say your capital D has become equals to 600 and your small d is 550 millimeters. Okay. Now we need to say, so now we have now fixed the dimensions. Now our dimensions are fixed for the beam. Now our dimensions is that your width of 500 and capital D of 600. So corresponding to that, there will be some dead load, and we are applying some live load also on the beam, such that we need to say what is the now actual bending moment that's applied on the beam external. So that we need to solve now further again. So I would say W dead, that is 25 kilonewton per meter cube into this dimension of 0.5 into 0.6. That 25 into 0.6, that's 7.2. 5, 6, 37.2. 7.2 kilonewton per meter. And we already know what is the live load we can apply on the beam. Do we know that? Live load was given to you 45 kilonewton per meter cube. 45 kilonewton per meter cube. So I would say, what is the total loads we can have? That's 45.7. That's 52.2 kilonewton per meter. And because of this, what is the factored external bending moment applied on the section? That is 1.5 times this loading, overall loading 52.2 into L square by 8. What was the L? L was 7 square by 8. So you would get a value of MUE equals to what you can say 480 kilonewton meter. This is the MU external final value. See, initially we don't know the value of D. Initially we don't know the value of D. Okay, capital D. We assumed the value of D to be 700, and corresponding to that value of D, we calculated the dead load. We calculated dead load, and from that we calculated overall external bending moments. And we said that corresponding to this condition, I'm saying that my load's external bending moments, it should be lesser than my limiting condition, such that if I increase now, once I got the value of D, I should increase the D by some amount such that it would become now under reinforced section. The reason for that is because the reason for that is because the reason is because, okay, once we got the D record, we increase it such that it becomes finally as under reinforced. Once I increase it from D of this value to this value, my section becomes under reinforced section. Under reinforced section. Under reinforced section. And for that, if I now fix that actual D should be 600, and corresponding to that, now I got external bending moments equals to 480 kilonewton meters. Now I need to say what is the actual neutral axis location. What is the actual neutral axis location? What is the actual neutral axis location? I am designing the section. Once I set the dimensions, see, now my dimensions have been set as 500 and this is 600, and we have some effective power also. And let's say that that small d is 550. D is 550. Now, corresponding to this section, there is some applied bending moment of 480 kilonewton meters. I want to see that if my section is now, I want to check now if my section is under reinforced or balanced or over reinforced. I have to check now what's the actual XU. Is it safe as a under reinforced section or is it not? So we need to see now. We need to verify that. We need to cross verify that. Let's try to verify that. I would say XU equals to 0.87 Fy AST. The bars we have 4 number of bars. Yeah, we don't know the value of AST till now. Do we know the value of AST? We don't know the value of AST. Then how can we verify it? We don't know the value of AST because we are designing it. We need to design the AST also. So how can you still get the value of XU to verify, to cross check it whether our solution is correct or not? Okay. See, we have equation of mu. We have equation of mu, and from that, if I equate that corresponding to external bending moment, and if I compare it with the limiting moment of resistance, I had to compare it with the limiting moment of resistance. Yeah, limiting moment of resistance. I have not compared that. Limiting moment of resistance. Why is that mu limiting? If I solve mu limiting, let's try to solve mu limiting. We would see what is the problem we can have. Yeah, mu limiting was this one. This was mu limiting. Mu limiting is Q times FCK BD square. So mu limiting, if I solve now, that is 0.133 FCK BD square, B and D square, small d square. 550 square, 500.133 into 30. That is 603.48 kilonewton meters. Okay. Now I would say finally our mu external is lesser than mu limiting. So this would ensure URS. This would ensure URS. If you still want that calculation of XU actual, where is the neutral axis location? I would say that we can equate from the external bending moments. That we can equate from the external bending moments. So if I write that equation of mu external equals to 0.36 FCKB XU D minus 0.42 XU. Can you get the value of XU corresponding to the moment that is applied equals to 480 kilonewton meters? And if I substitute the values of that FCK as 30, B as 500, and D as 550, and then solve the quadratic equation, you would get a value of actual location of neutral axis, that is at 188.85 millimeters. Then if I say what is the axial limiting we have, that is k times d, that is 0.46 times 550. For the FE 500 we have k equals to 0.46, and finally your limiting neutral axis location is 253, and that's, I would say, limiting condition is greater than xu, so under reinforced section. So that's proof both by both the things. This one is ensuring under reinforced, this one is also ensuring under reinforced. So this is one more check there. Now final problem was that design the section. Now we have to design the section. So I would say now my D has been fixed and capital D has been fixed corresponding to a given B. My D has been fixed, so I have designed the section. Now I need to design the steel also. Now I need to say what should be the amount of steel I have to provide. So that's our design. So we need to say what should be the what amount of steel I have to provide now. So this is the design of the steel. I need to say how much steel I have to provide, steel area in the cross section. Now since I got one thing from this XU and XU limiting, I got one thing. What was that? That section is under reinforced section. That means the AST required can be solved corresponding to the moments that are just external moments, not at limiting moments. But even we can solve this problem that we can, even if we provide only steel of AST equals to some value corresponding to external bending moments, your structure would be still under reinforcement and safe. Okay, let's try to solve that AST at the rate of mu external. AST would be required AST would be 0.5 FCK by Fy into BD into B was 500, capital small d was 550. You can see those values, and 1 minus under root 1 minus 4.6 external bending moments, actual external bending moments. Now because of the when we fixed the section of 500 and 600, and for that dead load was 7.2, such that final moments was 480 kilonewton meters. This is the factored 480 kilonewton meters. 480. So we can write 480 into 10 to the power 6 divided by FCK BD square, B and D square, small d square, and finally you would get a value of AST required equals to 1900. No, this is not that problem. This is some different problem. That is 2338.8 millimeters square. This is 2338.8 millimeters square, and we don't need to check whether this is lesser than AST limiting, because we already verified that XU was lesser than XU limiting, mu was lesser than mu limiting, and we are solving AST at the rate of XU, or we are solving AST at the rate of mu external. So that would be already lesser than AST limiting. That means the structure is under reinforced section. So once we got that AST limiting, we also can check those with respect to maximum and minimum values we have. One of the maximum value is that AST should not be more than 4% of BD. Should not be more than 4% of BD. 4% of BD. And this is one check, and it always, I would say, AST is always lesser than this value. And one more is that AST minimum should be 0.85 Fy. That's 0.85 by Fy. Some equation is there. 0.85 Fy BD. Okay. That one you can solve that. You would check what is the value of this one, and still it would be safe. Now once we got that AST 2338.8, now I have to select a bar that having those that we can have finally area of the steel. So we have to select a bar of some suitable dimensions, suitable diameter. Let's go for that. Okay, 2338.8. okay, let's try to have a bar. Now our section is that we designed the section with width of 500. Width is 500. Total depth is 600. Effective depth is 550. Effective cover is effective cover is 50. So at this location I have to place bars. I don't know the value of those is, I don't know the diameter of bars. So let's try to have, let's say I'm going to take, usually we take 20, 16 and 25. Let's take what you call as 25 bars. Let's take 25 millimeter diameter of the bars. And I would say, what is the number of bars we need? What is the number of bars we need? I would say that is AST required. AST required by area of one bar. Area of one bar. So AST required is 2338.8 divided by area of one bar would be pi by 4, 25 square. So that's almost equals to 4.7. So I would say you have to take 5 bars. You need to take 5 bars. So I would take 5 bars. Let's substitute those 5 bars here. 1 bar, 2 bar, 3 bar, 4 bar, 5 bar. And I would say this is your effective depth of D equals 550, and there's some effective cover of 50 millimeters. That means the clear cover would be equals to 50 minus the bar diameter of the bar divided by 2. This one, this is your clear cover, 37.5. Okay, this is your so this part, final part, we call as detailing of section. This is detailing. That means final thing is that one would design something. Final thing is that this is the final trophy, final gift we can have as a designer. So this is that thing. We have a beam of dimensions 500, 600, and the bars are placed from 50 millimeters center to center from the bottom. This is our final designing. That's called as detailing of that section. Detailing. Let's take problem number 10. Problem number 10. So our simply support beam is there. Simply support beam, and effective length is 7.5 meters, and there is some dead load and live load. So we say that live load is equals to 30 kilonewton per meter, live load. And we say that when it is live load, so it does not exclude, so it's excluding self weight. Self weight is separate and live load is different thing. Self weight is a dead load, and live load is moving load, or you call it as imposed load. And we need to design the beam. We need to design the beam for limit state of collapse in flexure. Limit state of collapse for flexure. So that's what we are doing, flexure. Okay, M20 Fe 415 are your material characteristic strengths, and your width of the cross section B is equals to 0.35. That means 350 millimeters. Okay, now we need to design the simply support beam. Let's take general value. Let's say this is our beam, and there's some width of 350 millimeters, and I don't know the value of capital D, and I don't know the value of small d, and some steel bars would be there. I don't know the value of those steel bars also. There's some steel AST. I don't know the value of D. So how can you design that if you don't know the value of those? So let's go for the general rule. We have general thumb rule for the calculation of D. That is a span by 10. That means 7500 millimeters divided by 10. That is 750. So it's an initial guess that we are going to take 750 millimeters. And if I calculate dead load corresponding to that, W dead, that would be 25 kilonewton per meter cube. And we have this BD. You have this BD 0.35 into 0.75 meter square, and you would get a value of 25.35 into 0.75, that is 6.56. (6.5625) kilonewton per meter. This is your dead load, and total load, we can say finally your total load would be such that your bending moment diagram, maximum peak we can have MU, I would say factored bending moment because of loads would be 1.5 WL square by 8. WL square by 8. What is the total W we can have? Total W is because of dead load and live load. 6.56. This is live load and plus 6.56 as dead load, kilonewton per meter. into what have length square by 8, length square by 8. This is your external factored bending moments applied on the cross section. That's equals to 385.6 kilonewton meters. Now I had to ensure that my limiting moment of resistance is even greater than your external bending moments. So that means your D should be greater than or let's say greater than MUE by Q times FCK B and under root of that. So you solve that. That means the D required should be greater than this one for the section to be under reinforced. For the section to be under reinforced, D should be required greater than this value what we can have from this equation. The MUE, what was the MUE? We have MUE 385.6 kilonewton, 385.6 10 to the power 6 Newton millimeters, and divided by Q. For the steel, that is Fe415, we have Fe415, and the value of Q is 0.138, 0.138, and the value of FCK was 20, and value of B was given to you as 350 millimeters. This was Newton per millimeter square, and this was millimeters, and this was root of that millimeter square. Yeah. So finally you would get the depth required. That should be less than equals to that should be less than 631.8 millimeters. Now we would say you can directly say, let's say D goes to 700, and you can assume some value, suitable value, or if you say I am going to take effective cover, if you take effective cover of 50 millimeters, then finally I would say let's take D equals to 675. Let's say that I'm going to take D as 675. You can take any suitable value, it's up to you, because you are a designer. It's all about you, what you can take. If you can take 670, 680. If it is failing, then you have to revise the section. Better is to take around 50, 60 millimeters more than the D required. So let's take that 675 millimeters. That means capital D would be 725 millimeters. But initially we have assumed some values of D as per thumb rule. As per thumb rule, what we have assumed, we have to see that. So assumed value initially was capital D was 750. So that means for section to be under reinforced, your D should be even lesser than the that assumed value 750. So we can finally assume that 725. So 725 is sufficient. I would say 725 would be sufficient. So now I got the section. There is some steel reinforcement. I don't know how much steel is to be required, but the D I know small d, that is 675, and capital D is 725. Okay, and we have cross section. That width of cross section was given to you 350 millimeters. Now I need to design that steel AST corresponding to this value. Corresponding to this condition, I have to get the value of AST. See, since we have kept the D greater than D required, that means it was directly as under reinforced section. So that means I can now directly say what is the AST? That should be AST at the rate of MU external. And if you solve for AST at the rate of external moments, that would be equals to 0.5 FCK by Fy into BD into BD into B into small d. Small d is your 675. BD into that bracket 1 minus root of 1 minus 4.6, and bending moment external bending moment, that is 385.6 10 to the power 6 divided by FCK BD square. FCK BD square BD square BD square BD square BD square B and D square, small d square, and you can solve that and you would reach to some AST that is equals to 1900 millimeter square. 1900 millimeter square. You can now verify whether AST, this is the AST required as per MU, as per external bending moment. You can see what should be the AST limiting also. You can check that also. That is corresponding to MU limiting, and that we can already calculate with respect to XU limiting. If you say that value would be equals to 0.36 FCK B and XU limiting. XU limiting is 0.48 corresponding to steel of Fe415, and D, capital D was small d was 675 divided by 0.87 Fy. So this is the AST limiting we can have. 0.36 FCKB XU limiting divided by 0.87 Fy. And AST limiting comes to be equals to 2261.4 millimeters square. Now you can compare the two values. You can compare the two values of AST. We would say that AST limiting is greater than AST required for under. That means the section should be under reinforced. Okay, that means you have to provide just this value of 1900 millimeters square. But now we have to use that some bars. Let's take the diameter of the bars as. So we have to take the bars diameter of the bars. Let's take the diameter of the bars as 25. So you have to, it's up to you how to, you have to ensure that that area is around that 1900 millimeters square. It should be a bit more than 1900 millimeters square, but it should not be lesser than this value. But to ensure that I should select a particular diameter of the bar such that our area would be such that it is around that 1900 millimeters square. If I select a 25 bar, I would say number of bars would be equals to 1900 millimeters square divided by area of one bar. So we require almost 4 bars. Finally, I would say 4 bars are required. It's almost some 3 point some value. You can say 4 bars are required. 4 bars. That means the area we provided, finally, it was required. It was the area required, AST required. Now, AST provided is equals to 4 times pi by 4, 25 square. So we are providing 4 bars of diameter 25. So that is equals to 1963.49. And that should be also less than AST limiting. That should be, because finally you are providing some value. You are not providing the required value. You are providing some value because of the diameter limitation. You are providing some value, and that should also be less than. This should be less than AST limiting. You have to see. This should be AST. This should be lesser than AST limiting. Sorry. Okay, this is also AST lesser than AST limiting. That means we can write okay, and we can apply those checks also. AST minimum. What is the AST minimum we can have? That we have equation 0.85 by Fy BD. If we substitute those values, we would say how much AST is minimum required. That is 350 millimeters of width, and your small d was coming to be 675 or 650. Small d was 675, and divided by Fy for the 415 Fe415. So AST minimum is 483.38 millimeters square. But we have provided finally that's 1963. That is greater. That is we have provided more, so it's okay. We have provided than minimum. That's okay. Now maximum condition is that AST maximum. AST maximum is that 0.4%, or we can say 0.4% of capital BD. Capital BD. So 4% of capital BD. B is your 350. Capital D was 675 plus 50, 725, and that value equals to 10150 millimeters square. That is 10,150. That is bigger value. So that's bigger than AST A provided. So that's also safe. So all those conditions are safe. So finally, I would say my steel would be provided this value, and we have 4 bars. So I would say final detailing of that bar would be we have this cross section of B equals to 350, and capital D is 725, and there's some effective cover of 50 millimeters, and we have placed 4 bars. We have placed 4 bars of diameter 25, and the effective cover is there 50, and small d is somewhere here, center to center. You have to show that center to center. It's not that in this. I have to show that up to center to center, 6 to 675, And this is your detailing of the section. Let's take problem 11. Let's go for 11. Problem number 11. 11 number problem. Here we have LSM. It's saying that used LSM, limit state method, for the beam, that is RC beam, reinforced concrete beam, and effective span, simply support beam, 6 meters. 6 meters effective span, simply support beam, that is having some UDL, and gamma concrete is 25 kilonewton per meter cube. It's saying that you have to adopt D by B equals to 2. You have to adopt this, and for given materials we have M20 and Fe 415. And one more condition is that it's saying that I have PT limiting equals to, limiting tensile percentage of steel is equals to 0.955 percentage. So that is equals to AST limiting divided by small bd into 100. This is provided to you, AST limiting. That means what is the value of AST limiting? We have provided to you, that we can calculate from this one. Okay. Now we need to design what you call as simply support beam. So there will be some cross section. There is some cross section of width B and small d as, and is it capital D's? Yeah, this value D, this is effective depth small d. So there's some value of small d that's given to you, and there's some steel also. So it is the up to the center of that steel. So small d is given to you. It's small d, effective span, effective depth. Now what we need to get? Yeah, we need to design this beam. There should be some depth and there should be some width, such that it is its ratio is 2. So we should start by that. And this one is that AST limiting is also provided to you. And loading I don't know, and that means loading you should also calculate what should be the loads we can apply on the beam. Yeah, loading is actually provided to you. See what the problem is saying about the loads. It's saying that we are applying support. The beam should support, simply support beam should support live load of 14 kilonewton per meter, and it should also support superimposed dead load equals to 9.5 kilonewton per meter. That means it's saying that we have some value of W on the beam such that equals to W live plus W dead load plus W self weight. It is superimposed dead load. It's only we have imposed some load, external dead load. We are applying some external dead load, and there will be some extra internal dead load also that we call as self weight. So overall W is there. So this is W all representing represent it by WA. So that is the sum of all those three. So we need to say what is the self weight we can have. What is the self weight we can have? What is the self weight we can have? Can you approximate the value of capital D by the general thumb rule such that you can get the self weight? Because you don't know the value of B and D, so you can use the general thumb rule. Let's use the general thumb rule. It says that capital D should be around span by 10. That means 600 millimeters. And based on that, I can say your self weight would be equals to 25 kilonewton per meter cube into some B into some span capital D 0.6. But B is still unknown. How can you now get the B? How can you now get the value of B? So we have to see, is there any thing talked about effective cover? So we need to how can it start now? All of the data you have to assume now, because it's not, anything is not given to you, so we have to assume some data by ourselves. Let's go for, if you are a designer, you have to assume some data, initial data. So it's giving that if I assume that capital D is 600 and there will be some steel here, let's say some steel is there and there is some effective cover also, I would say there's some effective cover EC, such that my small d is somewhere here, small d, and I have some b also here, small b, and I have given to you the ratio d by b equals to 2, and I need the value of b. I need the value of b. That means b should be d by 2. So I need actually now value of d, small d. I need the value of d from this one. So I had to assume some effective cover, and I had to assume some bar also. I had to assume this one. So if I assume some value of bar around 20 millimeters, 20 meter bar, if I assume, we can vary it still, we can vary it on the later time. If I assume that there is some bar having 20 millimeters diameter, and there's some effective cover, there's some clear cover also, let's say 35, 30, 40. Now I am going to, as per calculations, if there is clear cover of 25 and I take bar of I take a bar of 16 millimeter bar, we can take any other value also. Let's take any other value. Let's take as per our convenience. Let's say there is some clear cover, and let's take that. Finally, if I take clear cover of 50, effective cover of 50 directly without worrying too much, if I take effective cover of 50 without worrying too much, I would say your small d would be 550 and your b would be 550 by 2. This is directly, we don't have to worry about this. What we assume now, clear cover is there, there is some bar. It's a lot of that stuff. We don't have to worry about that. We would see that later. That's not a big issue. If you're getting too worried about that, you can go that by that way also. But that's a bit hectic. You could say I'm going to select some clear cover of 25 millimeters, 25 or 30 millimeters clear cover. Then there would be some bar of 20 or 25 millimeters diameter, such that your effective cover would be, so let's say 20 by 2. So you would get some effective cover. Then you say total d minus effective cover would be small d. That would be some value. Let's say you got some value of 42. So I would take as 50. It doesn't matter because we are starting the design. So we can take any general value. Let's say effective cover is 50 and small d would be 550 by, yeah, small d was 550, and I can now calculate the dead load. I can now calculate the dead load. So dead load would be 25 into what was that value of d? 550. So I would write 0.55 by 2, because we have given the condition b by d, d by b equals to 2, d by b equals to 2 into 0.6. So let's solve it. 25 into 0.55 into 0.6 divided by 2, 41250. This is your kilonewton per meter dead load. Then we can add this value in the two given values of 14 and 9.5. Let's add those two values also, 14 plus 9.5. So that means W all, which implies that W all is 27.6. So I would say W all is equals to 27.6250 kilonewton per meter, and that is the total loads we are applying, working loads on the beam, safe working loads, safe loads. So from that we can get the external bending moment that is factored. So I would say 1.5 m because of service loads, and that we can solve now. 1.5 into dead load of 27.6250 and length of what was the length of the beam? 6 meter. So 6 square by 8, WL square by 8. So you would say that 36 divided by 8 into 1.5, that's 186.46. Let's say 186.47 kilonewton meter. This is your moment external. Let's say this value we got 186.47 kilonewton meter. Now another thing is that you have to design this beam, but you have to ensure that your moments, now to start the beam, to start the design, you should ensure that section is under reinforced. So for that I would say your mu external should be lesser than limiting condition. Let's go for that. Let's go for that now. So let's go for the design state. So I would say moments because of external loads, that should be lesser than your limiting moment of resistance. So I would say D required should be greater than MUE by QFCK BD square, QFCK BD square. Okay. So finally, this is the equation. You already know that. Then you substitute the values. That means D should be greater than that root of. Substitute this value of 186.47 10 to the power 6 divided by Q. Which of the steel we are using? Q. We are using the steel of Fe415. Fe415. That means the value of Q is 0.148. FCK is M20. Is FCK M20? M20, yeah, M20. And value of B, we assumed some value. B was 550 by 2. Yeah, we are 550 by 2. Let's see what do you think, is it correct or not? Let us think, let us see whether this is correct or not. Let's see what you are going to say. Let's see what you are going to say. Let's see what you are going to say. If you solve it, you would get some value. Let's say you got some value. Then let's say that D value was equals to you got some value of D. Let's assume if this is correct, let's assume that you got some value of D. D was equals to, let's assume we would see your aptitude here and your reasoning. Let's say your D value here was 525 millimeters, and you said that let's take that value of capital D as 580 millimeters final value. If you finally adopt that value of capital small d as 580, then once you said that my dimensions are fixed, we have effective cover of 50. So capital D would be 630, and my B, I have assumed that 550 by 2. So that's 550 by 2. Is this correct? Now? So actually the B, we assumed our problem was saying that your B should be D by 2. In the initial case, B should be D by 2. But if we see here, we have capital D as 580, and B by 2 would be somewhere 290. So B would be somewhere 290, but your value of B is only 550 by 2. So you are solving capital D required at some value of B that is a function of D also. It's a function of D itself. You're solving a particular value of B, you're solving a particular value of D, but the value of D is itself here function B, and B is also a function of D also. So we have to convert, actually we have to keep this 550, we have to keep as a function of D. We have to keep it as a function of D. We don't know the value of D actually. Then after that we would say your B would be 550 by 2. So we have to convert it. So I would say this one is not a correct way to solve this part of the problem. So this part is not correct way. You can keep it in on a side of the problem, on the page of the what you have. So let's say the correct way would be in this fashion, that D should be required, that should be greater than mu by q times fck b and the root of that. This is the correct way. Then we have to substitute the value of b is equals to D required by 2. So we have to substitute the value of B as D required by 2. So I would say D required, if I have the equation that mu equals to q times fck bd square. Once I substitute the value of B as D by 2, so I would get that finally dq by 2 and q times fck equals to mu. So my equation would be D required is not in this fashion. I would say my D required would be 2 mu by q fck 1 by 3. Do you agree with that? This is the equation we can have for this one. If the B is a function of D, then we can have the equation here in this fashion. Do you agree with that? I think it's okay. Yeah, it was your external bending moments. So let's substitute the values now, and you can get the solution. 186.47. So you can solve that. 186 0.47 10 to the power 6 into that factor of 2 divided by Q value was 0.148 for Fe415 and FCK is 20 and you have 1 by 3 of that. That's your D required. D required should be greater than this one, and that value equals to, finally your value equals to 186.87. You got some value, let's say, let's solve that. I would say 186.47, 186.47, 10 power 6 into this factor of 2, and we have this 0.148 into FCK, 1 by 3rd of that, 501, 501. So D required should be greater than 501, 501.32. So we should adopt some value greater than 501. Initially, what was the value of D? We assumed, what was the value of D? We assumed some value what? So initially we assumed value of D was 550, but in this condition it's saying D should be greater than 501. That means we can also take 550 also. It is not a worry here. We can take the 550 also and check there at that condition also. So if I take the same value as per initial value, because we are increasing some 40-50 value millimeters, so we can, if I assume same value of D, if I now adopt the value of D to be, if I now adopt the value of D to be as if I adopt the value of D to be, let's go to some side, let's write here. If I adopt the value of D finally equals to 550, our D required was, that should have been greater than 501 point some value 32. So if I adopt the D to be 550 millimeters as per initial value, so B would be equals to 550 by 2, 550 by 2, that's 275, that's 275 millimeters. So you got the B also, and we said that effective cover would be 50, and that means capital D would be 600 millimeters. Yeah, 600 millimeters. And our trial was also starting from that span by 10. This was 6,000 millimeters by 10. That is also same. So there's no change. The assumed value we have, and that is sufficient to design this problem. So finally, I would say our cross section of the beam now looks like you have B equals to 275. We have this capital D of 600, and we have some effective cover, and steel is there, some steel is there, such that effective cover is 50, and small d is what do we have, 550. And now we need to get the AST. We need to get the AST now. Let's try to get the AST. So once we provided D greater than D required, so your AST would be corresponding to mu external at the rate of mu external. So the equation is 0.5 FCK by Fy into BD into BD into B into D small d 1 minus root of 1 minus 4.6 external bending moment. What was the external bending moment we had? External bending moment we had 186.47 10 to the power 6. This is 1 minus 4.6 mu by FCK BD square, FCK B into D square, small d square. So that's your equation for AST, and we can solve that, and you would get a value of AST equals to 1115 millimeter square. Now if we take a suitable diameter, if we adopt the diameter of the bar to be 25, if we take 25 bar, and you would say number of bars would be required 1115 divided by pi by 4, 20 square, and it's finally we finally say your bars would be, we are going to take 4 number of bars. If we say 1115 divided by 0.25 into 20 square divided by 20 square into 4, that was your 111 5 divided by 0.25 divided by pi divided by pi and divided by 20 square. 3.54 we are getting. So once we got 3.54, that means we are going to take 4 number of bars of diameter 25. Now we need to say how much AST we are providing. This was the AST required. We would say this is the AST required. Now we would say what is the AST we have provided. What is the AST we have provided? That is equals to 4 bars of diameter 25. Okay, and that value is equals to 1256.6 millimeters square. And we have to ensure that this provided value, this should be less than AST limiting. So let's try to calculate AST limiting. What is the value of AST limiting? Corresponding to XU limiting, we have this equation 0.36 FCK B. The value of B was equals to 275. Yeah, value of B was 275. 0.36 FCK B into XU. The value of XU, we have to take XU limiting, that's K times D, 0.48, and the factor of D. The value of D was, I think, 550. Yeah, divided by 0.87 Fy. 0.87 Fy into AST, that's your AST limiting. So you can get the AST limiting coming to be 1447.8 millimeters square. And now you compare AST versus AST limiting. Your AST provided is 1256.6 and limiting value is 1447. So this is I would say this condition is satisfied. So I would say okay, it is safe, or it's okay, that's URS. Section is under reinforced. So finally I am going to provide 4 number of bars and the dimensions we already know. So final detailing of that section would be we have a width of cross section 275 millimeters, and the capital D was 600 millimeters, smaller d was 550, and effective cover was what we call as 50, and we have 4 number of bars of diameter 25. So this is your detailing of that. Then we show those arrows, dimensioning of those, and that's all for this problem. This is all of this. And minimum, you can also check AST minimum. That's not a bigger task. AST minimum is 0.85 Fy BD. You solve this one and you would get some value. This would be 309 millimeters square. That's lesser than that AST provided. So minimum you have to provide. That means minimum you have to provide 309, but we have to provide also but we are providing 1256. That's safe. And AST maximum, this is never touched. I think it is never touched in the problems. 0.4, that is 4% BD, because it is possible only when you go for over reinforced section, and there's a possibility there where you might have 4%, but usually we don't have this 4% somewhere. Our limits, our value is always lesser than this value, 4% of BD. I think it is a capital D, 4% of capital D. This one is a capital D. Okay, let's go for problem number what you call as 9 to 12 problem number. This one is easy problem, 12 problem. Let's take problem number 12. That's your easy one. Problem number 12. It's saying you only need to get the lever arm. Get the lever arm, that is Z. Lever arm Z, that is D minus 0.42 XU. So for the section, we have section given to you. The section dimensions is that B equals to 250 and capital D is 400, and we have effective cover. Effective cover is 40 millimeters, and we have 3 bars of 16.5. 3 bars of 16.5. 3 bars of 16.5. And the conditions is that first condition is that we have M20 and we have Fe 250 mild steel. So for that I would say your Z would be D minus 0.42 XU, and we need to get the value of XU and we need to get the value of Z. Yeah, that what you call as D. Let's try to get the value of XU. XU corresponding to first state, that is 0.87 Fy AST divided by 0.36 FCK, and B also there. B is also there. B of 230 is it 230 250? Yeah, B is 250. Okay, That means XU equals to 190.8 that 72.8 millimeters, 72.88 millimeters. Now we need to see whether our that lever arm should be corresponding to limiting XU or it should be corresponding to XU, because our section should be, we always prefer under the reinforced section. So I should check that what's the limiting condition also. So XU equals to XU limiting equals to K times D, and for mild steel we have this 0.53 of that small d effective depth. So effective depth would be 360. Can we say that small d would be 360? 400 minus effective cover, so that is 360, and it comes out to be 190.8 millimeters. So section is under reinforced, so you can take X equals to XU actual 72.88. So let's write that Z equals to D minus 0.42 XU actual, and that value Z equals to 329.4 millimeters. And second part of the problem is that your material characteristic strengths, we have M25 Fe415. Yield strength of steel is 415, and that characteristic compressive strength is M25 for concrete. Let's go for that one. I would say, what is the value of X? U, that would be 0.87 Fy, and AST is fixed, 3 bars of 25, 3 bars of diameter 16, okay, divided by 0.36 FCK. FCK is M25 into B. Value of B was 250. So it comes out to be equals to 96.79 millimeters. And the value of K, the value of K would change because your steel grade has changed. So your axial limiting would be 0.48 times 360, and that value equals to 172.8 millimeters. And still, I would say this is your under reinforced section in this case also, because XU lesser than XU limiting, so your Z would be 360 minus 0.42 XU, actual XU, that's 96.79. So final value of Z equals to 319.36. Okay, let's go to problem 13. And after that we have only one problem left. So this is one of the most important problems you can have. This is the final design problem, 13 problem design. Singly reinforced beam, SRB, we can call it as SRB. That means steel is provided only in the tension zone, in the tensile zone, TC. Okay, we have a working moment is there, that is 210 kilonewton meter, and we have fixed the width. Because of some architectural constraints, your width is fixed as we can't vary the width, that's fixed as 230 millimeters, and your concrete is M25, steel is Fe415, and we have to design this one. So your B is fixed as 230. Now you need to get the capital D, small d, and some steel also. You need to get the steel also, and this is your designing. So let's say how much total applied moment is there on this cross section. Some sagging bending moment is MU factored applied. Let's say that what is the MU external applied, external factored bending moment, that is 1.5 times because of the dead load live load combinations, and 1.5 times that 210 kilonewton meters. So that's 200 and plus 5, that's 315 kilonewton meters. 210 into 1.5, 315 kilonewton meter. Okay, now our starting condition is always that your limiting moment of resistance should be greater than mu external, and for that we don't know the value of capital D, because I need that dimensions of D and B. So B is known to us, but I need value of small d. I need the value of small d because your limiting moment of resistance is the thing is that I can write it Q times FCK BD square, and that should be greater than MUE. So I don't know, I don't have to fix that capital D for. I don't have to use the thumb rule. Let's forget the thumb rule first. Let's say that we are directly using that MU limiting should be greater than MU external, and we are going to see what should be our calculations here. So I would say the D required would be greater than, it should be greater than MUE. Okay, this is your MUE divided by Q. What is the value of Q for Fe415? 0.138. Yeah, 0.138 is there. And FCK we have M25, and value of B was given to you, fixed value 230 millimeters. So you would solve that and you would get that D should be greater than, that effective depth should be equals to that 6, it should be greater than 630. It should be greater than 630 millimeters. Now see, if you are going to assume, see, you would say I am going to take 650. If you are going to take that, adopt that D equals to 650, that's almost closer to D required 630. That means there's lesser margin you have increased by, you have increased lesser value of that D, and in that case your condition would be such that you would face difficulties in what, in providing the steel. You would say, if you solve that AST at the rate of mu external, you would get some value. And I would say, let's have that direct. I'm not going to solve that in a proper way. I would go to just give a judge that what you call as gist, GIST gist. I'm going to give a little bit of that. Let's say that your AST at the rate of MUE you got when you solve this one, and you would get AST equals to 1642.4 millimeters square. And you are now taking that, you are taking 25 bar diameter of the bar, and you need, as per that, you need 4 number of bars. You need 4 number of bars. And once you said what was the area of the area provided for that, because of the 4 bars of diameter 25, your area provided was equals to 1963.43, 1963.49. But if you solve AST limiting, but if when you solve AST limiting for the same case at the rate of XU limiting, you would get a value of AST limiting coming to be 1788.78. That means in this case it has not ensured that under reinforced section. I would say AST limiting is lesser than AST provided, so this is over reinforced section, so we don't prefer that. So there is a problem with that, so we had to actually increase the depth. And if you still want to take that, because it has become over reinforced section because of one thing, that means you had used area of this, you had provided more area as compared to the limiting. You needed 1642, but you provided 1963 as per the diameter of the bars required, and it was greater than limiting. Now you want to say I'm going to take a few bars such that the area is a bit lesser. I would say if I take the bars in a way that my area is lesser than 1788 and it's more than 1642, so I have to adjust to that. For this case. If I say I have calculated that if I take 4 20 diameter bars and I take 2 16.5 bars, and corresponding to that area provided is equals to 1658.7 millimeters square. So this value, I would say, uh, this is between these two values. That needed value is 1642 and limiting value is 1788, and this one is, I think, safe. This one can be safe, but you have to guess that value. You have to select a number of bars. You have to take a number of iterations to get to this value now for this case. This is because once you substitute the value closer to the value required, your t value was required to be 630, but you assume it's 650, and based on that you needed such value of diameter of the bars which would be around between the value of required value and limiting value. So that's very critical. It would take you 5 minutes more, 2 3 minutes more to calculate that particular value. Okay, so that's why you always prefer diameter, that depth should be increased by some 50-60 millimeters. If you directly say that depth should be going to 630, I would take finally 680 or 700. Then after that I would calculate, and maybe the calculation would be easier. Calculations would become easier. calculations would become easier. Let's take that I'm going to take capital D, that small d, to 700 millimeters. Let's assume that I'm going to take capital D, that small d. Let's have that design also, final design. This was your initial part. If you try to keep that value of d to be 650, this was what was going to happen. Okay, now if I say, well, based on this one, if I substitute the value of d to be 700 millimeter, and I'm going to solve based on that, the AST required. I would say AST required is equals to 0.5 FCK by F. Yeah, AST we already know. AST already we know. Yeah, yeah. Let's go for that. Let's go for that. Let's go for that. I would say corresponding to this value, I want to say what is the AST required. AST required. So AST required is equals to 0.5 FCK by Fy. FCK was your, so FCK was 25 by Fy into BD. So B was given to you as 230, and you are using capital small d as 700. And we have this 1 minus root of 1 minus 4.6, and the external bending moment was equals to 315 kilonewton meters. 315 10 to the power 6 divided by what you have, FCK BD square. FCK BD square. BD square. Let's see what's the value we can get from this equation. That 1 minus 4.6 into 315 into 10 to the power 6 divided by 25 into 230 into 700 square. That 1 minus of that answer, and we have to multiply that 230 into 700 into 25 into 415 inverse into 0.5. 1469. So I need this much amount of steel. 1469.69, 7 millimeters square. So this is the amount of steel that I had to use now. AST required. So by changing the depth to 700, initially I said that the depth should be 650, and on that case my area of the steel was required 1642. And on this case I required steel equals to 1469, lesser than the initial case, because I have increased the depth. So AST required is this value. Now we can assume, if I try to assume that diameter of the bar is 20, let's say that the diameter of the bar is 25, which implies number of bars equals to answer divided by 0.25 divided by pi and divided by 20 square. That means the number of bars required is 4.6. That means 5 bars we have to require 5 bars. And if I solve that number of bars, 5 into 0.25 into pi into 20 square, and that comes to be 1570. 1570. So if I provided 5 bars, that means area provided is 1570.8 millimeters square. Now I want to see what is the AST limiting we have. What is the AST limiting corresponding to this? We need to calculate AST limiting, and for that AST limiting is corresponding to axial limiting. So I have to still calculate that now again. 0.36. So that's why I always prefer a D greater than this one by some margin, by some 50-60 millimeters more. If you got 630, you should go to some 680, 690. And in this case I took the value of 700, and because of it, your iterations would be lesser. You have to else you have to solve a lot of stuff there. So this was you already solved that AST limiting at this case, and it was some value. It is a function of D, because AST limiting is a function of axial limiting, and axial limiting is a function of K times D. And because of the D, it has changed, so your AST limiting would get changed. So that's why we are calculating that again. 0.36 FCK, and B, the value of B was given to you 230, and divided by 0.87 Fy, 0.87 Fy AST. This is our equation. Let's solve it. 0.36 FCK B divided by 0.87 fy. What is the missing parameter we have? Yeah, XU limiting is missing here. XU limiting. So that's your XU limiting. That's 0.5, 0.48 corresponding to 415. And the factor of D, the value of D, we assumed D to be 700, I think. 700. So we write that 700 here. So this factor we have to multiply 0.48 into 700. So the AST limiting is 1926.38 millimeters square. So you can see now there's more margin of that your required area is 1469 and your limiting value is 1926. So I think a difference of 500 millimeters square is there between the two. But if you compare the previous one, you can see the margin. You see the difference between the two. Required was 1642, but limiting condition was 1788. So only 100 millimeter square was difference because you selected D closer to the value of D required. That's the problem when you select D closer to the D required. So they always try to prefer D greater than D required more by some 50-60 millimeters. Okay, then now once I got the area provided, it is what I can say it's lesser than area limiting, so that is safe. Or I can say this is under reinforced section. Then finally this is your section of 5 bars. 1 2 3 4. Now there is one more condition here. There is one more concern here. Your bars won't be placed actually you are having 230 millimeters. If you are placing a bar of 20, you are placing a bar of 20 millimeters diameter, 20 millimeters, 20 20 20. So we are placing 5 bars. That means the diameter of one bar is 20 and 5 bars having 20 into 5. So 100 diameter, 100 millimeters is already accounted. Out of the total 230 width, you are placing 100 only of the steel. So we should also think that we should not overlap those bars. We should not overlap those bars. If we have 5 bars and there is the total dimensions of 230 and bars are accounting 100 millimeters out of that total line. If the total width is 230, out of that 100 is accounted by bars only. So you have to ensure that this thing is not going to happen there. We call this as congestion. There's a possibility of congestion of the beams. There should be such that there should be a spacing between the bars. There should be a shared spacing between the bars. I would say this method, you should not prefer this one. You should not prefer this one. We designed it, but it would be having a problem of congestion. It would be having a problem of congestion. The 5 bars should not be placed together in one line. If your width is lesser, that is 230. That means we should place the bars in rows. We should place these 5 bars in 2 rows, such that I would say my bars should be placed in this way. I can place the bars in this way. So this should be the final, I would say, configuration of the bars. This should be the final configuration of the bars. There should be some sort of detailing would be in this fashion. Now, if I make the final that detailing, I would say you had this bar of small d equals to 700, and we have 5 bars. Let's have 5 bars, 1 2 3 4 and 5. And I would say the spacing, the clear to clear spacing that we call as 30 by 2. So we can now assume some values here. Let's assume some values here. Now I can assume that if your concrete is M25, and minimum clear cover we already studied in the previous lecture, that what was the minimum clear cover we can have. Minimum clear cover required for M25 grade is 30 millimeters. So minimum you have to ensure that there is 30 millimeters of cover, clear cover. So I would say the clear cover should be minimum of 35. Minimum should be 30. Minimum 30 millimeters should be clear cover, CC. So I would take that 35. Let's take 35 millimeters of clear cover. 35 millimeters. If I take this 35, And the diameter of the bar is, what was the diameter we selected finally? What was the diameter we selected for our calculations? Yeah, 20 diameter we selected, 20 millimeters. 20 millimeters. So I would say this is 20. This is 20. And and the spacing between these two, center to center, not that, we would say this is clear to clear, clear. Yeah, this one we can take some 30 values. We can take this one as some value of 30, or some value of 30 by 2. Let's say this is some value of, you can take 20. Let's take 20 millimeters. 20 millimeters. And that means what? That means what? That means capital D gets affected. Capital, so that small d gets affected. Effective depth is the up to the, actually it's up to the center to the center distance of those centroid of those, what you call as bars. Actually it is the center to center of the centroid of the bars. But we can ignore that centroid of those bars. We can directly take that up to the center to center of those bars. Let's have that in this way. Let's try to have that in this way. Sorry. So up to this line, I'm going to take that small d. Up to the center line of those bars, that this is our small d, I'm going to take small d. So it's going to vary now. It's going to vary now. If I say this was your d, such that this d, I'm going to take this value equals to 700. And after that, I have to get the capital D. I would say so your capital D would be, I would take then finally, I would say, see how I am going to calculate capital D. I'm going to take this total of 20. I'm going to take this total of 20, spacing between spacing, vertical spacing between the bars, that is 20, and that means this center to center is 10. After that we have 20 diameter of the bar. After that we have clear cover of 35. So that means I'm going to take effective cover of 35 plus 20 plus 5, yeah, this 10, that's 55 plus 10, 65. So clear cover, effective cover of 65 is there. I would say there is effective cover of 65. So finally, I would say capital D is 765. Capital D of the bar is 765, and the width was restrained to 230 millimeters, and we have provided 5 bars of 25. This is your final detailing of the problem. There are different variations of the solution. You can select any of the different combinations. So one of the combination is that the solution of the problem was designed in some sort of way, in this way that your what you call as, we have six number of bars. We have six number of bars, and we have, out of that, four number of bars were of diameter 25, and two bars were 16.5. Corresponding to that D was 700 millimeters. This is one of the case we can also have. And out of those two bars, out of those six, we have two bars of 16.5 and four bars are of 25. This is one of the different approaches we can also have. But I assume that we are going to take same bars, same diameter of the bars as 5 number of 25 bars. So you should always try to prefer even number of bars, such that the placing of those bars is easier, because you have to fix the bars also. You should not place the bars in the, you are not keeping the bars in the air. So this method is also not preferable. The one which I showed, this is also not preferable. That it is easy to show that dots here. It's easy to show, but when you want to place that, it becomes difficult to place that when you are having 3 bars here, 2 bars here. How can you join that? So you need to have that, what you call as stirrups, and those, what you call as those bars which we join, which are used to help those tie bars, we can call them. So that's very difficult job to do. Always try to prefer we have even number of bars. Try to go with even number of bars, either 4, 6, 8, 4, 8, 6, or we can also go for 9. This should be the I would say variation of those bars. If you are going with this one, try to go with this one also. You can take the area required in this fashion also. Try to prefer this one. Try to prefer this one. And the area AST provided for this case is, you can check that also. AST required for this case, you can solve that. You can check that here. AST required for this case. Yeah, this was your 25. Okay, you can have different combinations. You can check different combinations. You can check different combinations. Let's go for final problem. Let's go for final problem. Let's take the final problem we can have, and that's your final problem of that singly reinforced beam. But in this problem, we are going to change the stress block. We are going to change the stress block. Initially, our assumed stress block stress strain variation was in this fashion. It was parabolic up to the strain of 0.02, and then it remained constant up to the failure strain of 0.0035. This was idealized stress block that was used during derivations. Now, in this problem, it's saying that you don't use this one, you go in this fashion. As per assumption 3, that is saying we can take triangular stress block, we can take trapezoidal, we can take rectangular, but that the results out of that, they should be in perfect agreement with the test results of that actual one. So if I am going to take that in this way, I would say your strain at this location where your compressive stress peak was developed, and that strain is 0.0010, and the strain at the failure is 0.0030 strain, and the stress here is 0.45 FCK. So this is the stress from the side. This is the final stress we have. So if you want to make the stress block out of it, I would say there is some strain variation, there is some strain variation, and there is some neutral axis, and there is some depth of neutral axis that we call as XU. And I would say the strain at the outermost compressive fiber, because this diagram is all about compressive test. This does not care about the flexure. This is all about compression test. It says that the extreme fiber is having compressive strain of 0.0030, and somewhere it would be having a value of, somewhere it would be having a value of 0.0010, and from that we can have the stress block. We can make the stress block also here. We can make the stress block. I would say your stresses from the strain of 0.0030 to 0.0010, we have a rectangular stress block. We can have a stress that is constant. That means the stress is constant up to this strain value of 0.0010. After that there is a linear variation of that stress strain, so that there is a linear variation up to the neutral axis. Finally it becomes 0 at the neutral axis. Then at the bottom of that tensile, where the tensile reinforcements are placed, there would be some T equals to 0.87 Fy AST, and there would be some net C acting somewhere, C net, so that we have to calculate, and the stress here is 0.45 FCK. This is your stress block. That is a bit different from the initial case that during the derivation we have. Then our data is that we have a what you call as, we have a simply support beam, and this is singly reinforced beam SRB, and the area of the steel is provided to you. AST equals to 1500 millimeters square. Width of the beam is 200 millimeters, and effective depth small d is equals to 400 millimeters. Effective depth 400 millimeters, and for that material we have 415 and M20. Now we need to get, the problem is saying get the neutral axis location, that is XU. Get the location of neutral axis. This is the location of XU, and you also get the moment of resistance of the section. Once you get the XU, you can get the MOR. So let's go for that. I would say, can you tell me this value of Y? Can you tell me this value of Y by the similar triangles? I would say we have this Y, we have the strain of 0.0030 for the depth of XU, for the depth of neutral axis XU, and I have the strain of 0.0010 for the depth of xu minus y. So value of y would be 3 by 7. 3 by 7. It's 2 by third of xu. You can check that also here. That is 3 times. So you can say that this is 3 by xu equals to xu. This is 1 by xu minus y. So you would get 3xu minus 3y equals to xu. So that y equals to 2 by third of xu. Y is 2 by third of xu. So that means the stress block is having those dimensions. This is your 2 by third, and this one is your 1 by third xu. And we can solve that. What you call as, we can solve the location of neutral axis xu. We can solve the neutral axis location. Can you solve the location of neutral axis? And how can I solve that? So if I equate that C equals to T by summation of forces in horizontal, I would say your C force is equals to, can you tell me what should be the value of C? I don't know the value of C. I have to calculate the value of C. The value of C would be, there is some C1 and there is some C2. Let's say there is some C1 and there is some C2. And resultant of that, those two is a value of capital C. So I would say value of C is equals to C1 plus C2. So I need to solve the C1 and C2. Let's solve that. Let's solve the C2 first, the rectangular part. I would say C2 is the area of the stress block into width of B. Area of the stress block into width of B. Into width of B. I would say area of the stress block is equals to that 0.45 FCK into that 2 by third of XU. And I have to multiply that B also. I have to multiply that B also. And C1 would be area of the triangle. It's a triangular variation. It's not parabolic. It's a triangular variation here. We say there is a triangular variation. This is triangular variation. It's not a parabolic variation. It's a triangular variation. And area of the triangle, we know. Area of the triangle, that's 1 by 2, 0.45 FCK. And the neutral axis, that 1 by third of XU. And multiply of B. And you have to sum them, C1 plus C2. That will equate to, you have to equate this one equals to T, 0.87 Fy AST. Okay, so you can get the value of XU. So you can get the value of XU, that would be equals to 0.375 FCK B. So finally, I would say your C value of total C force is equals to this one. This is your total C force. And what is the difference with respect to the that derived result during that derivation? What was the value we have in the actual derivation we have? That's total C force was 0.36 FCK BXU. So in this case, we have 0.37 FCK, 375 FCK BXU. And T force is same. So then we can solve that XU equals to 0.87 Fy AST divided by 0.375 FCK times B. Now you have to substitute those values to get the value of XU. Let's go for that. Value of Fy, that was your Fe415. And area of the steel was given to you as 1500 millimeter square. And the 0.375 is as it is. FCK was given to you as M20. And value of B was given to you as 200 millimeters. This was your Newton per millimeter square. This one was also megapascal. So finally you would get a value of XU equals to some millimeters, 361 millimeters, 361 millimeters, 361 millimeters, 361 millimeters, 361 millimeters, 361 millimeters. Then I would say moment of resistance would be C times Z or T times Z. So I would say that is some force of C. The value of C was, what was the value of C we have? C force was 0.375 FCK BXU. 0.375 FCK BXU. And the lever arm is D minus 0.42 XU. Is it correct? Is it correct? Now we need to say what is the lever arm. I think it is not correct. We have to see whether this is correct or not. So we don't know the value of lever arm. We need to calculate the value of lever arm. So for that, I need to get this value of xu. What is the location of xu? That we need to get the location of what you call as centroid of that C force x bar. That was initially it was 0.42 of xu, centroid of the in the actual derivation. There was 0.42 xu, centroid from the top. And in that case, we need to check that. We need to check that. So we had this rectangular portion and triangular portion. We need to calculate the centroid. Let's go for that. Let's go for that. I would say for the C2 force, let's say for the C2 force, let's remove all that stuff inside. Let's remove all that stuff inside. I would say C2 force is acting here and C1 force is acting here. And from the top, let's say the centroid is at x bar, and that is equals to C1 x1 plus C2 x2 divided by C1 plus C2. Can you say that? And C1 and C2 I already know. You can have those values C1 and C2 from this equation. And value of x1 and x2 you can calculate. The value of can you calculate value of x2? This is the value of x2. That is if the rectangular part was 2/3 of xu, this was 2/3 of xu, and this was 1/3 of xu. So for the 2/3 of xu, I would say your x2 bar would be x2 equals to 2/3 of xu, and we have centroid acting at 1/2 of that. 1/2 of that. And x1 would be equals to, this one is your x1. From this point to this point, this is your x1. This is our x1. And that would be equals to 2/3 of xu plus 1/3 of 1/3 of xu. So that's your x1 and that's your x2. And you solve that and you would get a centroid value of x bar equals to 0.422 xu. So initially it was 0.42 if you compare that with the previous result, 0.42 xu, but in this case we got 0.422. That's almost the same. 0.422 xu. Let's substitute those values and to get the value of MOR. So 0.37 FCK. FCK was your 20 megapascals. Value of B was given to you 200 millimeters. XU was given to you, that is solved, that you calculated 361. So you solved that 361, and the capital D, that effective depth was 400 minus 0.422 XU. So here the equation is 0.422 XU, lever arm XU. What is the value of XU? That's 361. So finally you get a moment of resistance equals to 134.1 kilonewton meters. So this is actually the lever arm can be shown in this way. Lever arm can be shown in this way, that if you had this beam, you have a specific general beam, and the T force is acting here, 0.87 Fi AST. So at that location, I would say center to center would be some bars having the AST equals to 1500 millimeters square, and there's some width of B equals to 200 millimeters, and the effective depth was small d 400 millimeters. And I would say neutral axis is somewhere here, and this was your 1/3 and 2/3 of XU, and we got the value of location of neutral axis XU. It was coming to be 361 millimeters, and I would say some C force is acting somewhere here at some x bar equals to 0.422 XU. That means the lever arm is the difference between CG of C force and CG of T force. So this is our lever arm, that is called as Z. That is the difference of D minus 0.422 XU. This is the lever arm. So moment of resistance can be either solved for T into Z, or we can say C into Z. So that's your moment of resistance. That was the end of the problems we have related to singly reinforced beam. Thank you for watching this series of RCC 1 reinforced cement concrete. Thank you for watching our series. Okay.